Okay, so this is the second part of the course, which is called optimization first derivative test. The first derivative test is associated with the slope of a graph of a function. Slope means derivative, like dy by dx. In other words, we can call it slope, which you studied in fundamental mathematics, like y2 minus y1 over x2 minus x1. This is just for your understanding. The derivative comes from the definition of slope anyways. So the first derivative is associated with the slope of the graph of a function at a point. It is reasonable to expect that the first derivative is also related to the properties of graph. We will see that how does it happens. Okay, in this section we examine how information about the first derivative reveals insight into the shape of the graph of a function. In particular, we study methods for finding absolute maxima and minima. What is actually absolute maxima and minima? Like we will develop some functions, like we did some functions in cost, revenue, and profit. So we want to know that at which point we will get the maximum profit, or at which point we will get the minimum cost. So everyone try to get the point where they can get maximum profit or minimum cost or minimum loss. So we use these tests. First derivative test and second derivative test is also the same thing, but a different approach, which tells us that at which point we can get the maximum profit, that how many products should we sell to get the maximum profit, or what should we do in order to minimize the cost. Sign charts will be used extensively in this chapter, which will help us to identify or to discuss the behavior of the function. It is suggested that you review the terminology and techniques for constructing sign charts found in section 2.3. And apart from that, one more thing I would like to say, that you should know what is domain and range. You can Google it, or I think we did this in fundamental mathematics as well. Domain and range. For example, we have a function f of x equals to 1 over x. Domain is the set of values where your function is defined. I can write here, domain is set of values where your function is defined. Like here in this function, this one, you can see that you can get result for f of x at any point of x except x equals to 0. If I say x equals to 0, f of 0, 1 by 0 equals to undefined. So other than x equals to 0, the domain is set of all real numbers except x equals to 0. We can write it as this: set equals to x belongs to set of all real numbers except 0. So we don't include 0. So this is called the domain. We can do some other examples as well, like mm, let's see, for example, I write another function. Let's say f of x equals to 1 over x square minus 1. So we know that we cannot divide anything by 0. So if f of x, uh, if I say that x square minus 1 equals to 0, x square equals to 1, from here I can get x equals to plus minus 1. So this function is undefined at x equals to 1 and minus 1, because if I substitute x equals to 1, it will be 0. If I substitute x equals to minus 1, again it will be 0. So we can say that the domain of this function is set of all real numbers except x equals to 1 and minus 1. So this is how we identify the domain of a function. I revise it once again. Domain is the set of all those values where your function is defined. So we will use this definition of domain and range, and you can take it as an assignment. I don't know, assignment number 7, you can say assignment number 7A, a special assignment apart from your regular lecture, and we can include this domain and range in your final exam as well. You should prepare it for that one, and you can search it and you can study about this more, and also we can discuss it in live tutorials as well. Okay, so the function f of x equals to x cubed minus 3x has the derivative. If I take the derivative of this function, it is 3x squared minus 3x, and further we can write it 3 equals to x plus 1 times x minus 1. The graph of the function, if I make the graph of this function, its graph is like this. The graph of a function and its sign chart are the derivative. For the derivative is shown. When the function will increase, the derivative will be positive. When function is increasing from here till here, you can see that this is graph of a function. The function is going upward, it is increasing. The derivative is positive. You can see that f dash of x is positive, plus 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 till minus 1. This is minus 1. Till minus 1 the derivative is increasing, and after minus 1 till minus 1 the function is increasing. After minus 1 the function is decreasing, so derivative will be negative. So you can see that from minus 1 to 1, derivative function is decreasing, so derivative is negative from minus 1 to 1. So you can see from minus 1 to 1 the derivative is negative. Afterwards again function is increasing, so our derivative is positive. So from here we can conclude that if function is increasing, derivative like f dash of x will be positive, and if function is decreasing, then derivative is negative. So you can see that when scanning from left to right on intervals where the graph rises, the derivative is positive. So you can see that here derivative is positive where the function is increasing, like you can see that I change the color, it would be better to see. From here function is increasing, here function is increasing. So in these areas from minus 1 till here the derivative is positive, and from 1 to onwards derivative is again positive because function is again increasing. So this is the same thing which is written on the interval where the graph falls, the derivative is negative. You can see that here on the interval where the graph falls, the derivative is negative. From here they are talking about now this section. You can see that the function is decreasing, some function is falling down, or so called decreasing from minus 1 to 1. From minus 1 to 1 function is decreasing, so derivative is negative. You can see that it is negative. So when x equals to minus 1 and 1, the derivative is 0. So at x equals to 1 and minus 1, the derivative is 0. This is called point of inflection or extrema. We can discuss it later. We can put f dash of x equals to 0. From here we can get x equals to 1 and minus 1. So derivative is 0 at that point. You can see that at x equals to minus 1 and 1, derivative is 0. Okay, now this is the formal definition which we have already discussed for interval AB. If f dash of x, if f dash is greater than 0, then f is increasing. If, or in other words, if f is increasing, if function is increasing, if function is going upward, f dash will be positive, like positive. And if function is decreasing, then f dash will be negative. Or if f dash is greater than 0, then we can say that function is increasing, and if f dash is negative, then we will say that function is decreasing on that interval. So here you can see that f dash of x is positive, it means function is increasing. Graph will write like you can see example here. Graph will be maybe in this form, in this form, in this form. In all these forms you can see that it is increasing. If f dash is negative, then function will decrease, fall, then its shape will be like this. In all forms you can see that it is decreasing. Here we can see that intervals on which the function is increasing or decreasing, given the function f of x equals to this, which values of x corresponds to horizontal tangent line. Horizontal tangent lines are where f dash is 0. We take its derivative, f dash of x is 8 minus 2x. We put f dash of x equals to 0. 8 minus 2x equals to 0. So from here we can get x equals to 4. So this is a tangent line on a graph which values of x corresponds to a horizontal tangent. So x equals to 4 corresponds to a horizontal tangent. You can see that we put the derivative equals to 0 and we get x equals to 4. A horizontal tangent line exists at one x value, namely x equals to 4. For which values of x the function is increasing or decreasing. So we have discussed it before that if f dash is greater than 0, then function will increase, and if f dash is less than 0, function will decrease. So f dash of x of this function is 8 minus 2x. So if we put f dash greater than 0, it implies that 8 minus 2x greater than 0, or 8 greater than 2x, or 4 greater than x, or x less than 0, or x less than 4. So when x is less than 4, function will increase, because f dash we got this x less than 4 from this when f dash is greater than 0. So the function will increase from minus infinity to 4, because less than 4 it can go to the minus infinity, and function will increase when f dash of x is greater than 0, less than 0. So we can see that 8 minus 2x less than 0. From here we can conclude that x is greater than 8. So from 4 till positive infinity, the function will increase. So here you can see that is what we have done now. F of x is increasing when derivative is positive, that is what we have just discussed. So we can put f dash greater than 0, we can conclude that x is less than 4, and f is increasing whenever x is less than 4, f is decreasing when f dash of x is less than 0. So f dash of x equals to this, and here we can get those intervals where the function is increasing or decreasing. Okay, so the given function f of x is this. Sketch the graph of f at any horizontal tangent line. So we already checked that the horizontal tangent line, when f dash of x equals to 0, from here we got x equals to 4, and we have already said that horizontal tangent line exists at x equals to 4. So here you can see that 1 2 3 4. So this is the top of a function, and here horizontal tangent line exists at point where x equals to 4. Here this is point x equals to 4, so we draw a tangent line which is the peak of the function. So the graph with the horizontal tangent line is shown in the red. Note that horizontal tangent line when x equals to 4. Okay, definition of critical numbers. There is a definition of partition number as well. We can discuss both. A real number x in the domain of f. Now here the word comes domain. We have already discussed in the beginning of this lecture. A real number x in the domain of f such that f dash of x equals to 0, or f dash of x does not exist. These two things are very important. Does not exist or 0, then it is called a critical number of f. And if it exists in the domain of f, right? So here the critical numbers of f that are in the domain of f are partition numbers for f dash. We can also call them partition numbers, but all partition numbers cannot be critical numbers because they should be in the domain of f. What does it mean? We can discuss it later. F dash may have partition numbers that do not belong to the domain of f, so are not critical numbers. Uh, so we can discuss this thing in an example. That what does it mean? That all partition numbers may not be critical numbers, but all critical numbers are partition numbers. When building a sign chart, we need all partition numbers of the derivative of f dash. So if a polynomial, then both partition numbers for f dash and the critical numbers of f or the solution of f dash equals to 0. For example, here uh, f of x equals to 1 plus x cube. Find the critical numbers of f, the intervals on which f is increasing and those on which f is decreasing. So first of all, we take its derivative, which is 3x square. So from here we can get x equals to 0. When we put f dash equals to 0, it gives us x equals to 0. Find the critical numbers of f on the interval. Now this x is in the domain of f, so it is also, this is a partition number and also a critical number. So f of x and f dash of x is positive before and after 0. Plus 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 plus. How do we know that it is positive before and after 0? Before 0 we can choose, let's say, -2, so f dash is positive. If I say x equals to 2, again f dash is greater than 0, so it is positive before and after, so f is increasing before and after. We first find the partition number for f dash of x, and to do so we need to take its derivative and put it equals to 0 and solve it for x. We solve f dash of x equals to 0. F dash of x gives us x equals to 0. The partition number x equals to 0 for f dash is in the domain of f, so 0 is the only critical number of f. So this is very important statement, that since 0 is in the domain of f, so it is a critical number as well. The sign chart for f dash is shown that f is increasing either before 0 or after 0. How do we make this sign chart? You should know. Before 0 you can choose any number. Let's say before 0 we choose x equals to -1, and we see that f dash of minus 1 is 3 minus 1 2, which is a positive number. So that is why we have all the positive. You can choose any number before 0, it will give you a positive derivatives. Similarly, if you choose any number after 0, again it will be a positive number. Okay, so f is continuous at x equals 0, so f is increasing every day. Okay, this is very important example to understand. We have said that where f dash of f equal to 0 or where f dash does not exist. Here we take its derivative, we get this number. Now f dash of x does not exist if I substitute x equals to 1. So x equals to 1 is a partition number. Now we will see that is x equals to 1 is in the domain of f. Yes, x equals to 1 is in the domain of f, because we can, if we substitute x equals to 1 into this function, we can get f of x equals to 0. So we have a solution for f of x when x equals to 1, which says that it is in the domain of f. So we can say that this is a partition number and a critical number. The derivative f dash is continuous for all x except x equal to 1, which gives a 0 in denominator. Since the numerator is constant, f dash of x not equals to 0 for any x, it follows that x equals to 1 is the only partition number for f dash, and since x equals to 1 is in the domain of f, so x equals to 1 is the only partition number for, is the only, here we should write critical number, because critical number for f dash. Okay, partition numbers for f dash and critical numbers for f. You can see here sign chart, you can choose any number for x before 1 and after 1 it is negative, so it is decreasing function for this. So sign chart indicates that f dash is not defined at x equals to 1. So the sign chart also indicates that f is decreasing on minus 1 to 1 and also again 1 to infinity. Since f of x is continuous, so f of x is decreasing for all x. Here you can see that it is decreasing and continues decreasing. Okay, so here we can see another function, and we can take its derivative, find the critical numbers. When we take its derivative, it will be minus x minus 2 whole square, so x equals to 2 will be the partition number. Now since x equals to 2 is not in the domain of this function, x equals to is not in the domain of this function, because if I substitute x equals 2 into this function, f of x is not defined. So x equals to 2 is a partition number, but it is not a critical number. So here you can see that we write f of x as a power. So when we take its derivative, it will become minus 1 over x minus 2. To find the partition number for f dash, note that f dash is non-zero for all x and is undefined at x equals to 2. So x equals to 2 is the only partition number for f dash, and since x equals to 2 is not in the domain of this function, so it is not a critical number. Since x equals to 2 is not in the domain of f, so it is not a critical number for f. So the function f has no critical numbers. So here you can take another assignment, write some functions, write some functions who have partition numbers but not critical numbers, like we have this example. So f is decreasing from minus infinity to 2 and 2 to infinity, and these are defined at x equals to 2. So now local extrema. When the graph of a continuous function changes from rising to falling or high point, or a local maxima occurs when the and vice versa. When the graph changes from falling to rising or a low point to high point, then is local minima. Like here you can see that graph is decreasing, so this is local minima. Further decreasing, this is also local minima. Now it is increasing, this is local maxima. Then decreasing, this is local minima. Increasing, maximum, maximum, minimum, minimum. So the high point at c3, this is c3, c6, and the low point c2, c4 are not the highest or lowest of all points on the graph. They are the highest and lowest point of x value here. Local extrema. F of x, f of c is called the local maximum if there is an interval containing c such that f of x less than equals to f of c for all x in this domain. This is exactly the same thing for local maxima and local minima. And f of c is called local minima if there is an interval and then containing c such that f of x is greater than f of c. We can discuss it through an example which would be more simple and easy for you. And local extrema and critical numbers. F of c is the local extrema of a function f, then c is a critical number of f. The theorem states that the local extrema can occur only at a critical number. The theorem states that local extrema can occur only at a critical number, means those numbers should be in the domain of that function. It does not imply that every critical number produces a local extrema. So here, very important thing, the first derivative test. How we will apply first derivative test? Very simple. If f dash of x exists on both sides of a critical number c, the sign of f dash can be used to determine whether the point is a local maxima and local minima or neither. Case 1, when f dash of x changes from negative to positive at c, then f of c the local minima. This is very important statement. We will use it in an example. And here you can see that when f dash of x changes its sign from negative to positive, then we will say that it is local negative to positive, then it is local maxima at c. And if it is that is local minima. Conclusion, that is local minima. You see that it is decreasing at this point and then start increasing. So this is the local minima when it is negative, decreasing and then increasing. So it is local minima. And for local maxima, again the same thing, when it changes its sign from positive to negative, so it is local maxima. Like when f of x is increasing and then decreasing, that is local maximum. You can see that it is increasing and then decreasing. So conclusion, local, this is local maximum. So the first derivative test increasing with no sign changes, it means that there is no local maxima or minima if there is no sign change before and after critical number. So then there would be no local maximum. Like here, no sign change before and after, so it is local. There is no local maxima. You can see example like this, like here. Okay, that is again the same thing. If it is negative before and after, again no sign change, so it is also neither maxima or minima. We jump into some examples. For a function equals to 0, x in horizontal tangent, we have already discussed. This is the same thing. Uh, I just want to jump into some examples because these are some unnecessary details. Locate local extrema. Find the critical number of f. So first of all, we take its derivative. I take its derivative 3x square minus 12x plus 9. We put it equals to 0. So it will be like this. And if I factorize it, minus 3x minus x plus 3. So x minus 3 minus 1 x minus 3 equals to 0. So x minus 3 x minus 1 equals to 0. So x equals to 3 and x equals to 1. So x equals to 3 and x equals to 1 is a partition number and it is in the domain of this function. So these are critical numbers as well. So we draw a line. We write here 1 and 3. Now I choose a number before 1 and after 1 and I substitute them into the derivative, and let's see is derivative is positive or negative. So before 1 we can make a sign chart here, like before 1 I can say 0. This is x. I substitute 0 into the derivative. If I substitute 0 into the derivative, it is 0 minus 0 plus 9. So plus 9 means that f of 0 is positive. So here we have positive. Before 0 is before 1 is positive. Now after 1 I can substitute 2 and I check that if dash of 2 is positive or negative. 2. So 12 minus 24 plus 9. 12 plus 9 is 21. So it is minus 3, which means that f dash is negative after 1. So it is negative. Now before 3 we can consider 2. Now after 3 we can consider 4. So I think it is positive. So you can see that at 1 f dash is positive. So it means that f is increasing and then decreasing, then again increasing because here negative and here is positive. So at x equals to 1 it is local maxima because function is first increasing then decreasing, and at x equals to 3 the function is first decreasing and then increasing, so it is minima at 3. Find the critical numbers. We have already find the critical numbers. Find the local maxima and minima of f. We have already found that at x equals to 1 it is maxima and at x equals to 3 it is minima. We can sketch the graph. How do we sketch the graph? As I said, from negative infinity to 1 function is increasing, like function is increasing till 1 it is increasing, and then till 3 it is decreasing, and after 3 at 3 it is 0, then again it is increasing. So we can see that find all numbers x in the domain of f where either f dash of x equals 0 or f dash does not exist. So here when we solve this we get x equals to 1 or x equals to 3, like we have already discussed this. F dash of x exists for all x critical numbers of f where x equals to 1 and 3. So here find the local maxima and minimum of f partition numbers for f dash of x, x equals to 1 and x equals to 3. When we make this sign chart, as I have already explained, how do we make this sign chart? We substitute numbers before 1. We have chosen 0 and after 1 we have chosen 2, and we saw that it was like this. So there is a local maxima at x equals to 1 because f dash of x first increasing then decreasing. So local maxima at x equals to 1 and then local minima for 3. So we can now sketch the graph. You can see that function is increasing till 1. Function was increasing till 1 and function was here at x equals to 1 we have tangent, and at x equals to 3 we have tangent. So at x equals to 1, if we substitute x equals to 1, 1 minus 6 plus 9 plus 1, 10, 11 and 5, you can see that this is the local tangent. So graph will go up till here and then it is decreasing up till here. So like this we draw our local tangents. That is why we draw, so that we can make a suitable graph. Okay, so for polynomials, if this is a polynomial function, then f has most n x intercept and n minus 1 local extrema, either minima or maxima. That is so called irrelevant. We can go through from this through an example. Now here we can discuss some examples related to economics. This is the graph of a derivative. When derivative is positive, function is increasing, right? You see that from this point till x equals to 10, or we can say that from here up till here x equals to 30, derivative is positive. So it means that function is increasing. Function is increasing, like function is increasing, and then after 30 the derivative is decreasing, which means that function is no, not like that. You can see that below this line derivative is negative. It means that from up till 10 function is decreasing. Up till 10 function is decreasing. Then from 10 to 50 derivative is positive, so function is increasing up till 50. After 50 derivative is negative because it goes downward, then again function is decreasing. So this is the graph of a function. When derivative is positive, function is increasing. When derivative is negative, function is decreasing. From here to here derivative was negative, so we can say the function is decreasing. When from here to here derivative is positive because it is above the line, so it means that from 10 to 50 function is increasing, and then derivative is negative, so it means that function is decreasing. The graph shows that the approximate rate of change of the price of egg over 70 months period, where E of t is the price of dozen egg and t is time in months. Determine whether the price of eggs was rising or falling and sketch the possible graph for E of t. So through this graph we can make the possible graph for E of t, which we have already did. So you can see that here is the graph. You can see that this is the graph which we have already discussed, that till 10 derivative was negative, so function is decreasing till 10. From 10 to 50, 10, 20, 30, 40, 50, the function was increasing, and after 50 again it is decreasing. So you can draw an approximate graph, not 100% accurate. The graph of E of t will be decreasing when t less than 10, and when t is greater than 0 it will be again decreasing.